Good morning, everyone. Today we'll probably we can finish the series analysis, or at least on Wednesday we will finish that, and then we'll go to the next topic. Last week we talked about the power series. Okay, use the power series to express your solution. Okay, so suppose your solution, the power series y, is this summation. And then I need to take the first derivative and the second derivative. Then this is an example. I want to find the solution about 0. So in that case, I know that my solution is this one. Okay. Taking the derivatives, then I bring this back to our original differential equation. Then we need to rearrange that. We put all the power in one summation and then compare the coefficients. Then we will see we have recursive relations about the coefficients. Okay, and once we have the initial, once we have some coefficients like A2, A3 is 0, then we can get the rest of the coefficients. Okay, so now let's do one more example. So I have a I have a differential equation. In this case, in the past, we probably need to find the homogeneous solution and then the particular solution. With the particular solution, then we can guess this is polynomial. So my particular solution should be also polynomial. Okay, but now let's use the power series to express this solution. So first, suppose we want a power series solution. We want a power series solution. And this power series solution is, when we have a power series, we need to know it's a series about what point. Okay, and in this case, it's a power series about 0. So x minus 0 to the n, there'll be about 0. Okay. Then y double prime, if y is this, then y double prime will be n times n minus 1 an x to the n minus 2. And this n is from 2 to infinity. And then x, here x squared, and then y prime will be n times an x to the n minus 1. And this n is from 1 to infinity. And plus 4y. So y is this series, n from 0 to infinity, an x to the n. That should be equal to 1 minus x squared. All right. So now you can see the power. I have n minus 2, n minus 1, and n. So you need to choose one. Okay, you need to make it as the same power. Then you can compare the coefficient. So you can either do all this will be n minus 2, or just n minus 1, or you pick this one. So this time let's pick x to the n. In that case, I can shift all the n to 0. So the first one, if this is x to the n, n minus 2 becomes n, becomes a new n. Okay, so your n should be m plus 2. Okay, so here your a will be a m plus 2. And then your n becomes m plus 2. M minus 1 becomes m plus 1. And your n is from 0 to infinity. Right? Because now, again, m minus 2 equals n. So when n equals 2, your capital N, this should be 0. All right. So here, this 2, they are the same. I shift the index. So shifting indices. Next. So x n minus 1 becomes x to the n. So I have summation. Then I want x to the n. So again, n minus 1 becomes n. Your n becomes 1 plus n, or n plus 1. So here n should be n plus 1, n plus 1. Should be n plus 1, a to the n plus 1. Right? n minus 1 becomes n. So your m will be n plus 1. And your n should be n plus 1. When n equals 1, this should be from 2 to infinity. So this n should be 2 to infinity. Okay. Then the rest a n. I still put x to the n. So this equals 1 minus x squared. Is that correct? So this is the green part. So now next we can combine all the coefficients with the power to the n. So combine the summations from n equals 2. Well, remember that if you try to combine these summations, this n is from 2 to infinity. This is from 0 to infinity. Here, this is from 0 to infinity. So when I try to combine the summations, then I should do the n from 2 to infinity. Okay, because when n equals 1, there is nothing for the middle series. Okay, so when n equals 2, that means this one I have n equals 0 plus n equals 1, and then do the summation n from 2 to infinity. Okay, so what is n equals 0? When n equals 0, I have 2 times a2 times x to the 0. 2 times a2 times x to the 0. When n equals 1, we have 3 times 2 times a3 x. Okay, when n equals 1. So 1, there will be 3, 2, a3 x. And for this part, when n equals 0, 4 times a naught x. When n equals 1, I have 4 times a1 times, this is x to the 0, this is x to the 1. Then the rest will be n from 2 to infinity. N plus 2 times n plus 1, we just copy that, a n plus 2. And then n plus 1, a to the n plus 1 plus 4an x to the n. That should be 1 minus x squared. Okay, so now we can compare the coefficients. Okay, compare the coefficients. We have 2a, 2a2 plus 4a naught, that's 1. Okay, so this one should be here and this. And for x1, x to the 1, I don't have x to the 1 here, so it should be 0. So 6a3 plus 481 is 0. So this one is for x to the 0, this one is x to the 1, and next is x to the 2. So when n equals 2, I have 12 a4 plus, when n equals 2, 3a3 plus 4a2, that's minus 1. All right, and the rest, x to the 3, 4, 5, the higher power, there'll be O0. So this should be 0. Okay. The rest, n plus 2 times n plus 1, a m plus 2. Also n plus 1, a m plus 1. And 4an, that's 0. And then this, we have a m plus 2 will be equal to, the denominator will be n plus 2 times n plus 1. Numerator minus 4a n minus n plus 1 a n plus 1. you see this coefficient. This coefficient depends on the previous two coefficients. So this is called like two-term recurrence relative. And from this simultaneous equations, we can get A2 will be 1/2 minus 2A0. And A3 will be minus 2/3 A1. And if you want to find A4, A4 will be minus 1 minus 4A2 minus 3A3. That's equal to, first A2 will be minus 1 minus 4 1/2 minus 2A0 minus 3 minus 2/3 A1. I will get minus 1 minus 2 plus 8A0 minus 3 plus 2A1. That will be minus 6 plus 2A1 plus 8A0. Minus 6A2. Okay. Minus 6, 8A0, 2A1. And then for A5, you can use this two-term recurrence relative to find A5. Okay. Well, I have x squared here, right? So here is not correct, though otherwise I just feel that it's weird. Okay, I have x squared. Okay, so here should be x m plus 1. M plus 1 becomes n. N should be 1 minus n. So here I should have m minus 1 a to the m minus 1. And here we have m minus 1 times a m minus 1. Here I have A1 plus 4A2. M minus 1. So here M minus 1, A, M minus 1. A4 will be 4A2 plus A1 divided by 12. And your A5 will be 4A3 plus 2A2 divided by 20. So you can see that the coefficients depends on the previous two coefficients. Any questions for this? Now let's just see one more example about this power series. As so far you can see that for the power series, there is no difficulty about solving that. It is just a tedious work. So you need to be patient and manage those index. Okay. So for this example, suppose I also want the power series solution about 0. Then suppose we want a power series solution. And also this solution is about 0. And maybe because later on you have your initial conditions, and the initial conditions is at x equals 0. Otherwise, you can have this power series about 1, 2, whatever the point you want to expand. Then y double prime. For y double prime, I have n times n minus 1 an x to the n minus 2. And your n is from 2 to infinity. And then I have x y prime n times an x to the n minus 1. Your n is from 1 to infinity. And then minus y, so minus the summation an x to the n, that's equal to e to the 3x. Right here is e to the 3x. Remember that we can also expand this, express this exponential in Taylor series. So here that's 3 to the n divided by n factorial x to the n from 0 to infinity. This is also called Maclaurin expansion of e to the 3x. And then we need to shift the index. Okay, so how do we shift the index? We try to make everything starting from n. I mean, the power should be all in n. Okay, so if I shift the indices, this time I say n prime equals n minus 2. Well, the good thing here is that x times x to the n minus 1. This is also x to the n, right? I have x to the n, x to the n, x to the n. So I only need to change that x n minus 2 becomes x to the n. In that case, your original n is 2 plus n. So here your n is n plus 2. N plus 2 and here n plus 1. Your n from 0 to infinity. So when you shift, that gives you n plus 2 times n plus 1 a to the n plus 2 x to the n. And your n is from 0 to infinity. And the rest you just copy that. So n times an times x to the n minus n from 0 to infinity an times x to the n, and the right hand side the next step is that I combine this coefficient. Okay, so now let's combine the coefficient. So I have a summation. Well, n from 0, n from 1, 0, 0, so I should choose n from 1 to infinity. Here, n from 1 to infinity. Then I have m plus 2 times m plus 1, the first term, and the middle one. Oh, there'll be n minus 1 times an, right? So this 2. So here is n minus 1 times an. This is the coefficient for x to the n. And then remember that since I have the summation from 1 to infinity, so I have some additional terms. When n equals 0, here I have 2a2. When a equals 0, I have a naught, so minus a naught. Okay, since I'm going to compare the coefficients, so on the right hand side, I also need the summation from 1 to infinity. So I have, this is summation from 1 to infinity. Then when n equals 0, I get 1. So you can compare this coefficient with this series, this summation. And then 2a2 minus 1 minus a naught should be equal to 1. Okay. (2a2) minus a naught is 1. Now I get a2. It's 1 plus a naught divided by 2. And when n is greater than 0, that means for n equals 1, 2 to infinity, we have this recursive term m plus 2 times m plus 1 times a, this a is m plus 2. And then add m minus 1 times an. That should be equal to the coefficients on the right hand side, 3 to the n divided by n factorial. So you get your a m plus 2. That's 3 to the n divided by n factorial minus m minus 1 an, and the denominator is m plus 2 times m plus 1. Again, this n is from 1 to infinity. Any questions for this? So far, for those differential equations, those functions are analytic. We just avoid anything that may make the solution divergent. So suppose for this differential equation, I have a fraction, and this fraction may make the final solution divergent. Then what should we do? So first, let's talk about the ordinary point. What is ordinary point? So if I have a differential equation, the ordinary differential equation in this form, okay, I have a p of x times y double prime plus q of x, the function of x times y prime, and the r of x times y equals the forcing term. Now suppose p of x naught is not 0. If I'm plugging x naught, this is not 0. And then if I divide it by p of x, q over p, r over p, and also f over p, if those terms are analytic at x naught, then we said x naught is an ordinary point. Otherwise, we say x naught is a singular point. For example, f of x is x minus 3 to the power 5 over 3. And then if I take the derivative twice, I will get x minus 3, x equals 3 in the denominator. And then when x equals 3, it doesn't exist. So since the denominator will go to 0 and overall it goes to infinity, then it is not analytic, and we say x equals 3 is not an ordinary point, so it is a singular point. Okay, so now once we know how do we describe or distinguish or verify the x naught an ordinary point or not, then next step, if the x naught is a singular point, actually for the singular point, we can also divide it into two parts, a regular singular point or irregular singular point. So first, let's see the regular singular point. Since this expression, the fraction, is not analytic, now I just multiply a term, x minus x naught, and also x minus x naught squared. In this case, if they are analytic at x naught, then we will say this point is regular singular point. Otherwise, it is called irregular singular point. Okay, so here is an example. This is the differential equation, and I would like to check x equals minus 1. This point is a singular point or not. So here we can see that the qx is 2x, and then px is x plus 1, and then rx is 5x. So here apparently you can see that in the denominator, when x equals minus 1, this fraction goes to infinity. So x equals minus 1 is a singular point because it is not analytic. So since it is a singular point, now we need to check if it is a regular singular point or irregular singular point. So that's times the factor x plus 1 to this fraction q over p, and also x plus 1 squared times the r over p. In this case, we see this is 2x, and here we have a 5x times x plus 1. Therefore, those are analytic. So analytic at x equals minus 1. There's no denominator something term here. So x equals minus 1 is a regular singular point. Okay? Next example, I have a differential equation. And then first, I just divide by, well, we need to check what Qx is and Px is, and also Rx. So the Qx is 2x, and then Px is this term, x plus 1 squared. And then Rx is 5. So apparently in these two fractions, it is a singular point at x equals minus 1. So I should say here, x equals minus 1 is a singular point. Now, since it is a singular point, we need to check if it is a regular singular point or irregular singular point. So first, let's check this term. I times the factor x plus 1. Once I times x plus 1, I still have something in the denominator. And when x equals minus 1, the denominator is 0. And overall, this fraction goes to infinity. So it is not analytic. Therefore, x equals minus 1 is irregular singular point. Okay. Next example, I have my p of x, q of x, and also my r of x. So here we can have this fraction q over p, and this is r over p. In this case, see the denominator. When x equals 0 or x equals 2, the denominator will go to 0, which means that the overall, this fraction goes to infinity. So x equals 0 and 2 are the singular points because this is not analytic. And other points were just the ordinary points. Okay, so we need to check, since 0 is singular point, 2 is also a singular point, then we need to check if 0 is a regular singular point or irregular singular point. Same thing applies to 2. So first, let's check 2. Okay, so if I want to check 2, I need to time the factor x minus 2 and x minus 2 squared to each fraction, and we check. In this case, even though we have something in the denominator, but we focus on 2. Okay, when x equals 2, you plug into this fraction. It is analytic, so x equals 2 is a regular singular point. Now let's check 0. For 0, then I need to times x and also x squared. So once I times x and x squared, in this case, when x equals 0, I will still get the denominator is 0, and overall it is infinite. So this is not analytic. Not analytic at 0. So x equals 0 is an irregular singular point. All right, so now what happens if x is a regular singular point or irregular singular point? Because overall, we would like to find the solution of the ordinary differential equation. So if the x is a regular singular point, we can also try to find the solution. But in this case, we need to use Frobenius series rather than power series. So the Frobenius series here, that means that there may be no power series at x naught for our regular singular point. So we may consider another series called Frobenius series. So what is the Frobenius series? the Frobenius series is in this form. The y is the linear combination of x minus the x naught, and but here the power is m plus r. Okay, rather than just n. So if I have this series as my solution y, then we can bring it to our ordinary differential equation. So to bring this series to the ordinary differential equation, then we need to figure out what y prime is and also y double prime. So y prime, you take the derivative, and using the chain rule, you will get m plus r, and also the power will be m plus r minus 1. The n is still from 0 to infinity. Okay, because if you put 0, I have r here. Okay, so it is not 1. Your n is still from 0. Same thing that if you take a derivative again, then you have this additional term, and also your power will be same but minus 1 again, so you get minus 2. Okay, so let's just use this Frobenius series to find a solution. Here is an example. For this differential equation, you can check 0. Actually, 0 is a regular singular point. So since 0 is a regular singular point, then we can use the Frobenius solution. Here's the Frobenius series. Okay, so consider my solution is y is equal to this linear combination. Because x naught is 0, so here is 0, so that's why we only have x to the n plus r. Then you bring this back to y, and you take the derivative, and you can plug in to y prime and also y double prime. Okay, so here you can see the abbreviation is in the second line. You will rearrange it, then you will get, since this overall this is equal to 0 and the x cannot be 0, so the one way is their coefficient should be 0 and this coefficient should be 0. So first, let's check this coefficient. This coefficient should be 0, and this equation is called indicial equation. From this indicial equation, we can get r is either 1 or minus 1 over 2. So if it is 1, let's see, if it is 1, we also have another condition here. So we can plug in 1 to our second equation. Then you have the relationship between your coefficient Cn. So when r equals 1, you can see the iteration. So Cn will equals to something of the previous one. Like C5 is something with C4, C3 is something to C2. In this case, first we can find that if I have a C0, then we can get C1. C1 is something C0, and C2 is like something C1, and since C1 is something C0, so actually for all the coefficients later on, it can be expressed in terms of C0. So here the C1 is, for example, minus 6 over 5 C0. And then you can get one of the solutions, y1. When r equals minus 1/2, I have another relationship. Okay, and in this case, C0 equals 0. And when C0 equals 0, then the next one, C2, will be 0, because then everything will be 0. So the second solution is like C0 times x to the minus 1/2. And then you have a linear combination of these two, C1 and C2, no, Y1 and Y2, then you'll get your general solution. Okay, and here you can see that my R, I may have two values since I have two solutions y1 and y2. So I should have R1 and R2. So let's check the R1 and R2. So suppose that 0 is a regular singular point of the differential equation, the ordinary differential equation, and then the R1, R2 are the roots of the initial equation. And we assume that R1 is greater than or equal to R2. Then we have three different types. First, R1 minus R2 is not an integer. In this case, if the subtraction is not an integer, then I have the solution. It is called like two linearly independent Frobenius solutions. So the y1 is the Frobenius series, and here I plus R1. For y2, we also have here x to the m, but we plus R2. And your coefficient is not 0. The other condition is that what if R1 minus R2 equals 0? In this case, my y1, that is x m plus R1. But my second solution, well, related to the first solution, is y1, but I times the natural log. And later on, I also have a series. This series is the x to the n plus R1, and this n is from 1 to infinity. That is the case when R1 minus R2 is 0. The next one is that the difference is a positive integer. It's either that not any integer, I have a solution. If it is equal to 0, I have another expression. But if the difference is a positive integer, because it could be negative, it could not be negative because we assume that R1 is greater than or equal to R2. So since it is a positive integer, then first solution y1, same thing. But the second solution, I will have like a k, and then times the y1 and also the natural log. And the second term, here I have x to the m plus R2, and n is from 0. So we will have these three types and three conditions for our initial equations. And then later on, you can find a solution. So next, let's see this differential equation. First, well, to save the time, well, in the beginning, we still need to determine if I want to have a solution about 0. I want the series about 0, expansion about 0. Then I need to check if 0 is an ordinary point or regular or singular point. And you can check by yourself it is a singular point. And once it is a singular point, then we need to figure out it is a regular singular point or irregular singular point. If it is regular singular point, then we can use Frobenius series. If it is irregular singular point, that's beyond our scope. Okay, you will learn that later or in the future, not in this course. Okay. So you can check that 0 is a regular singular point. So now we can use Frobenius series. Okay, so now for the Frobenius series, again, this is our solution. Okay, and here this is the expansion about a point. Now the power will be m plus r. Okay, then once you remember this, then you can take the derivative to get the first derivative expression, and then the second derivatives expression. Okay, so now let's see here. Once you bring it back to the original equation, you should have this equation. Okay, so at home, you can try to plug in back to the original differential equation and simplify it to see if you can get this equation. Okay, if not, then ask TA or me. All right. So suppose now you know this equation, and then we assume that C naught is not 0. Then this time here we have an indicial equation, right? So the indicial equation that's r minus 1 minus 2. This should be 0. So we have two answers, R1 and R2. You can see that R1 is 2. R2 is minus 1. And you need to find the difference. The difference here is 3. Okay, 2 minus 1. So now we need to figure out when r equals 1, what is our relation? R equals 2, then what is our relation? And since the difference is an integer, so since it is an integer, our solution should be in this form. y1 and then y2 depends on y1. Okay? So first, if R1 is 2, then we have, so this becomes 2, 2, 2. This coefficient becomes m plus 2, m plus 1, cn plus m plus 1, cn, cn minus 1, minus 2 cn equals 0. And then your n is from 1, 2, 3 to infinity. Okay, great. And then from this equation, we can get the relationships between Cn and Cn minus 1. Okay? So we have Cn, that's m plus 1 divided by n times m plus 3, Cn minus 1. That means my first solution, y1, is c naught x squared 1 minus 1/2 x plus 3 over 20 times x squared minus 1 over 30 times x cubed, and then next term 1 over 168 times x to the 4th, and so on. Okay? Make sure that at home you need to derive this equation. Okay? Right, now once we have y1, we need to figure out the y2. So to figure out y2, this example will show us that why we should have this expression. Okay, so if we don't have that expression, first we think of y2 as this summation, this series, this summation. Okay, you can find Actually, the Cn star is this relationships with Cn minus 1 star. But you can see that I have, well, in the denominator, when n equals 3, that goes to 0, which means that it is not defined. At n equals 3. If it is not defined at n equals 3, that means I cannot find C3 or even C4, C5, because C4 depends on C3, C5 depends on C4. But if I don't have C1, then I cannot find C4 or C5 and so on. So in that case, I cannot find C4 star, C5, and Cn. Actually, it's a Cn star with n greater than or equal to 3. And that's why we say that someone was really brilliant and, well, probably just forbiddeness. So that's why it's called forbiddeness series. So he thought, he found out that y2 could be in this expression. Okay, instead of just Cn, this series, this summation, I add one more term. Okay. So if I add this one more term, this is my solution for y2. Since it is y2, you should know what y2 prom is. And also y double prom too. Right? And then you bring it back to the original differential equation. So as you can see that it is a tedious work. Okay, you bring this back to the original equation. You have here. And from at home, that you really need to do that at least one time. Okay. So here, first term and this term and the last term should be 0. Okay, if they add them together, it should be 0 because they satisfy the original differential equation. Why? Because what is our original differential equation? X squared y double prom plus x squared y prom minus 2y equals 0. Okay. So I have x squared y1 double prom plus x squared y prom minus 2y1. That's 0. Okay. Then, since they are 0, how about the rest equation, rest terms? We just choose that C naught star equals 1. No any reason, just for convenience. So when you rearrange that, you will see the following term. So here we choose K equals C2 star, and we say that this is 0. Also for convenience. From this part, C1 could be expressed in terms of C naught star. So C1 is minus 1/2 C naught star and C4 minus 1/2 C3 star, and C5 star will be minus 3/10 C4 star, and that's 3/20 C3 star. So everything you can see that so far, when n is greater than or equal to 3, that can express that in terms of C3 star. Okay, because C6 you'll get that's something C5 star, and C5 star is a portion of the C3 star. Okay, so you can also get this C6 in terms of C3. Then your Y2 equals C0 star 1/x minus 1/2 C0 star plus C3 star Y1/x. We can also let the C3 star equals 0. So the C2 will be C0 star 1/x minus 1/2. Then finally, the general solution. Yx will be C1 Y1 plus C2 Y2. Any questions for this? Those are the coefficients, right? So those coefficients, you can see that the right hand side is 0. So I have to choose that all the coefficients should be 0. Okay, this is already 0. And that's why here we have this expression. And C2 is 0. And since C2 is 0, that cancels out. I have a K. Then here I choose K equals 0. Okay. What if K is not 0? Because in this case, K just be 0. Great. What if K is not 0? If K is not 0, in this example, let's see. Again, 0 is regular singular point. Okay, so we will have a solution, a series solution about 0. So now this is for business series. So here we can see that my indicial equation here, r squared minus r should be 0. Okay, r squared minus r should be 0. So I have r1 1, r2 0, and the difference is 1, which is a positive integer. First, R1 is 1. Let's see the relations between those coefficients. So that R equals 1. I have Cn, because when R equals 1 here, n plus 1, I have n plus n Cn equals Wow, I didn't notice that. This should be last year. Cn minus 1. So we have Cn equals 1 divided by n times n plus 1, Cn minus 1. And this n is from 1, 2, 3 to infinity. This relationship means that what is the Cn minus 1? N becomes n minus 1. So here we have 1, n becomes n minus 1. So here n minus 1. N plus 1 becomes n. And this will be Cn minus 2. So in that case, actually Cn will be 1 divided by n factorial, n plus 1 factorial C naught. You can do like Cn minus 2 to Cn minus 3. And Cn minus 3 equals something for Cn minus 4. Finally, you can get this pattern that should be n factorial times n plus 1 factorial. Okay? So I can get my y1, that is always easier, C naught summation n from 0 to infinity 1 divided by n factorial n plus 1 factorial x n plus 1. Since the difference of the roots of the initial equation is an positive integer, so my second solution y2 will be k y1 natural log of x plus summation n from 0 to infinity Cn star xn. Then again, you need to bring this back to the original equation here. So you need to find y2 prom and also y2 double prom. You will get 2k y1 prom minus k over x y1 prom plus the summation n times n minus 1 Cn star x n minus 1, and n is from 2 to infinity. And the last term Cn star x to the n, n from 0 to infinity. That should be 0. We can choose C naught star equals 1. Again, that this part will be 0, okay, because they satisfy the original differential equation. We have k minus C naught star plus, make sure that at home during your free time, probably Saturday or Sunday whole morning, then you need to derive it by yourself. So the second term, n times n plus 1 Cn plus 1 star minus Cn star times xn, that should be 0. So apparently this should be 0 and this coefficient should be 0 because I have to satisfy the right hand side. So k, instead of 0, now k is C naught star, and C2 will be 1/2 C1 star minus 3/4 C naught star. C3 star will be 1 over 12 C1 star minus 7 over 36 C naught star. And then C4 star will be 1 over 144 C1 star minus 35 divided by, there's a big, huge number. Then your x2 will be C naught star y1 natural log of x plus C naught star plus C1 star x minus 3 over 4 C naught star x squared. And so on. We have a typo. This should be 2. Okay. And then how do you deal with this y1 prime y1? We know the solution for y1, right? So you just plug in. Okay, you substitute y1 and y1 prime with the expression that you found. And then you compare the coefficients. Okay?